Hello everyone and welcome to my presentation on seismic isolation system. Today, I will discuss how these systems are used to protect structure from earthquake damage through innovative engineering techniques. What is a seismic isolation system? A seismic isolation system designed to protect buildings and infrastructure from earthquake forces. Essentially, it reduces the amount of ground motion that gets transferred to the structure, isolating it from the shaking caused by an earthquake. This isolation helps protect the building and reduces the chances of damage during seismic events. Seismic isolation works by installing insulators such as rubber bearings, sliding bearings, or spring damper system between the building's foundation and the structure above it. These isolators allows the building to move independently of the ground, which lessens the shaking force on the structure and helps it remain stable. This is the block diagram of the closed-loop control system used in our seismic isolation model. In a closed-loop system, there is constant feedback that adjusts the system's response to external disturbance, in this case, earthquake forces. The diagram here shows how the input signals, which represent seismic force, goes through a controller, then the seismic isolation system, and then feedbacks into the controller. This feedback loop is essential in adjusting the systems in real time to mitigate the effects of seismic motion on the structure. To further understand the components and forces at play, here are the mechanicals and free body diagrams of the seismic isolation system. The mechanical diagram shows the layout and the connections of components like springs, dampers, and bearings, while the free body diagram focuses on the forces acting on each part of the system. These diagrams help us analyze how the system counters seismic forces, as each component plays a role in dissipating energy and reducing structural stress. Now, let's look at the closed-loop simulation run in Simulink. In this setup, we use a proportional integral derivative (PID) controller, which is critical in stabilizing the building's response to seismic forces. The PID controller continuously adjusts the system to balance seismic energy, enabling the structure to withstand shocks more effectively. In our simulation, this setup allows us to observe the system's control response, where adjustment happens instantly as seismic input changes. In this part of the simulation, we apply a step input to mimic a sudden seismic shock, and the graph here shows the step response output. This step response indicates how quickly and smoothly the system can return to a stable state after a seismic disturbance. A well-designed seismic isolation system should have a controlled, non-oscillatory response with minimal vibration after the initial shocks, as seen here. In contrast to the previous slide, this simulation shows an open-loop setup, meaning there's no feedback or PID controller. With no control adjustment, the system reacts more passively to seismic inputs. This simulation highlights how the absence of feedback in an open-loop system allows for greater movement and instability in the structure during an earthquake, which could lead to more damage. This reinforces the importance of closed-loop control for maintaining stability. Next, the responses of the closed-loop and open-loop systems was compared to the same step input. As you can see, the closed-loop system with the PID controller exhibits a smoother and a more controlled response. In contrast, the open-loop system lacks control and shows great oscillations. This comparison demonstrates how closed-loop control is essential for reducing building movement and ensuring stability during seismic events. To analyze system stability further, we use MATLAB to plot the poles and zeros as well as the step responses of our seismic isolation system. The poles and zeros give us insight into the system's natural behavior and responses characteristic. By examining the location of poles on the complex plane, we can determine how stable or unstable the system is. The step response here confirms that with appropriate control, the system returns to equilibrium quickly after a disturbance. Two key parameters we focus on here are the damping ratio and natural frequency. The damping ratio indicates how quickly oscillations in the system die out after a shock, while the natural frequency measures how often the system oscillates when disturbed. For an effective seismic isolation system, We want a high damping ratio to minimize vibrations, along with a suitable natural frequency that doesn't amplify seismic forces. The damping ratio here ensures that the system responds without excessive oscillations, aiding stability. The transfer function for both the PID control and open loop system. On the left, we see the PID control function, which includes the proportional, integral, and derivative terms for real-time adjustment, enhancing stability. On the right is the open loop function, which lacks feedback control, resulting in a less stable response to seismic inputs. Comparing this highlights the role of PID control in achieving a stable, resilient system. Next, we have the transfer function for the closed loop system with PID control. This function incorporates feedback, allowing the system to adjust continuously to maintain stability during seismic events. This calculation illustrates how the closed loop system, with its feedback mechanism, provides a more controlled and stable response compared to the open loop system. After that, for a more rigorous stability check, we also applied the Routh-Hurwitz criterion. This criterion evaluates the stability of control system by analyzing the characteristic polynomial. For our system, there were no signs changes in the Routh array, indicating that all poles are on the left half plane, meaning the system is stable. This analysis confirms that our design, including the PID control, ensures the system's resilience to seismic forces. In summary, seismic isolation systems are crucial in enhancing structural resilience during earthquake by decoupling buildings from ground motions. Through the use of isolators, this system mitigate the transfers of seismic forces, thus preserving structural integrity. Our analysis using closed-loop and open-loop simulation in Simulink demonstrates the effectiveness of PID control in achieving stability and desired responses. Calculations, including stability assessment through the Routh-Hurwitz criterion, confirm system stability and also affirming the viability of seismic isolation in structural protection. Thank you all for your attention and interest in this presentation on seismic isolation system. I hope it offers valuable insights into the importance of control systems in enhancing structural stability during earthquakes. Understanding and implementing the systems can make a significant difference in protecting lives and infrastructure. Thank you again for being a part of this session.